Okay, so we're going to talk about LeChatlier's principle in this presentation. And LeChatlier's principle basically says that if you place a stress on a system in equilibrium, the system is going to move in a direction that relieves the stress. So let's go back to our mental picture here. I've got a divided aquarium, and I want to know which way this system is going to move. So one way of looking at deciding which way something is going to move is something called a reaction quotient. We're going to develop this. So intuitively here, you know, there's more fish on the reactant side. I know that the fish want to spread out and divide themselves evenly. So I expect things to shift from the reactants towards the products. So keep that in mind that I had one product fish and it looks like 9 reactant fish. So the reaction quotient is something that used to be in our textbook but isn't anymore. Maybe it was too mathematical, but I still like it. And the reaction quotient works exactly the same as an equilibrium constant, but we just use Q when we're questioning whether we may or may not be at equilibrium. So if I compare the products over reactants and look at this, so I think if I selected this, so terrible drawing here. Let's see, I had one product fish and I had 9 reactant fish. So my ratio was 1/9, and we were expecting the value of K was equal to 1. So that 1/9 is less than the one I was expecting. So if Q is less than K, it's going to shift towards the products. And you intuitively knew that from just looking at that mixture, that there were too many fish on the reactant side. In the reverse, if the situation was flipped and I had lots of products, then I would have a 9-to-1 ratio. So then I would have a Q that was bigger than K, and if Q is bigger than K, it's got to shift back towards reactants. Another way I look at this is I just almost imagine my ratio being my divided aquarium here. So I know I've got to get to a 1-to-1 ratio. So the way I can do that is I can transfer fish out of my denominator and into my numerator, and in that direction, let's say it's products over reactants, so I'm removing reactants and placing them in the products. So that kind of also explains how this works. Okay, so we're going to play a little game here of equilibrium or not. So I've got a system, and we've got an equilibrium constant value for this, and I've got some concentrations that I've measured, and I want to know, am I at equilibrium or not? So let's take a look. When I plug these numbers in, I get my Q. So I wrote Q because I wasn't sure. And I get 1.0. Now 1.0 and 1.3 aren't the same thing. So that means that I am not at equilibrium. My Q is less than K. So that means I need to be shifting towards the products again. Let's try this again. So Q is less than K, shift. Okay, try it again. Here's another situation. I've got a phosphorus pentachloride decomposition. I've got a Kc of 1.8, and I've got a mixture that may or may not be at equilibrium, so I'm going to write a Q. And I get 4 when I plug all those numbers in. So 4 is not 1.8. If I was at equilibrium, then that Q would be equal to my K. So it's too big. That means that in order for this to work, if I think about this as just a 4-to-1 ratio and I want to get down to a 1.8 ratio to 1, then that means I've got to shift things out of the numerator and into the denominator, so I'm shifting back towards my reactants. Okay, so more often than not, what we're doing is we're considering these things, what things will affect our mixture. So let's take a look at if I add fish to the reactant side, what's going to happen. So I end up with too many fish on the reactant side, so some of them are going to shift over to the product side, and I'm going to reestablish my equilibrium. If I added fish to the product side, the same sort of thing is going to happen. I end up with too much fish or too many fish on the product side, and I'm going to shift back to my reactants. Okay, so let's look at a chemical system here. So I'm going to add nitrogen to this system. And nitrogen is a reactant, so I'm adding reactant to the system. So if I add reactant, it's going to shift towards the products. If I add hydrogen, hydrogen is a reactant again, it's going to shift towards the products. If I add ammonia, for some reason, ammonia is a product, so adding ammonia to this is actually going to be counterproductive. It's going to shift it back towards the reactants if I do that. Okay, heat is another factor. This process here is an exothermic process, so heat is a product. If it was an endothermic process, then heat would be on the reactant side. So in this case, it's on the product side. So let's turn up the temperature here. So I'm increasing the temperature, I'm adding heat. So if I'm adding heat, I'm effectively adding a product, and this would shift that reaction back towards the reactants. So let's see what would happen if I decrease the temperature. So if rather than putting a Bunsen burner under this, I put this in an ice bath, then what I'm doing is I'm removing heat. So I'm removing a product. So if I'm removing a product, that means that I'm taking away from that side, decreasing the fish on the product side. So some more fish are going to swim over from the reactant side. It's going to shift it towards the products. There's one more effect here, and it's not that hard to figure out. And what I'm going to do is imagine that I've got an equilibrium system here where I've got 1 liter total volume, and I've got 1 mole of every reactant and product in here. So their concentrations are 1 mole per liter. And I'm going to pretend that this is at equilibrium. So if that is the case, then when I plug all those numbers in, my equilibrium constant value is 1. So let's see what happens when I decrease the volume of the container. So if I squish that container down to half of its volume, I've still got the same number of moles at that instant of my reactants and products, and I decided I had 1 mole of each. So I've got 1 mole in half a liter, so the concentrations are now doubled by having the volume. So when I plug all those numbers into the equilibrium constant expression, I get a different number. I get 0.25. So I'm not at equilibrium. That's why I wrote Q, because I kind of had a question about whether that was going to be the case. Q is less than K, so that means it's got to shift towards the products. So that's the mathematical way of looking at this. Probably an easier way of looking at this is to count reactant moles and product moles. So I've got 1 mole of nitrogen, or effectively the coefficient on nitrogen is 1, on hydrogen is 3, and on ammonia is 2. So if I decrease the volume, I'm effectively kind of jamming these molecules in, and their way of creating more elbow room, as I usually like to think about it, is that they combine to make fewer moles. So I've got 4 moles of reactant molecules and only 2 moles of product molecules. So it's going to shift to the smaller number. So that may be on the product side, it may be on the reactant side. You may even run into a reaction where the number of moles on the left and right sides of the equilibrium arrow are equal. So in that case, decreasing the volume would have no effect on the equilibrium position if there was equal number of moles. But in this case, I've got more moles on the reactant side than on the product side. So that's the direction of my shift towards the fewer number of moles.